Back. We're still talking about general computer systems, and the point of this video is to learn some hardware terminology. Yeah, that's it. It's not exciting, but it is necessary. What is exciting is that you will most likely have heard many of the terms we cover in this video, and you're going to start to see all of these things start coming together. Last time we described a finite state machine, which I've drawn to the left here. The number of states and paths is not important. What is important is that this FSM, or finite state machine, has many paths or operations, right? You'll see operation 1, 2, and 3, and they all return back to the start, which makes a continuous loop, so no matter the operation, right? And we talked about how we are going to provide operation codes to tell it which of those paths to execute. Now, hanging out at the bottom right is the program memory, which stores the sequence of opcodes, which I've symbolized with the 3 curly arrows originating and returning to program memory. So that's like the sequence of opcodes. And you will download your program into program memory, and it will be read by your finite state machine. Now, the execution of a particular instruction takes place on the individual path. I've indicated this with a horizontal bar, right? And everything beneath this bar is the instruction execution, which we talked about last time. Right? Now, this state machine must also have the functionality to get the opcodes from program memory. The FSM, or the state machine, is going to take on a 3-stage architecture. So this first stage, or the top state, there is the fetch state, which means to grab the opcode from program memory. The word fetch is a very specific word to this subject. It's not my word, and it's always going to be called fetch. So again, the fetch state is going to retrieve or fetch that opcode from the program memory. The state right after that is called the decode state. And the decode state determines the path or the instruction to execute, right? Which one of those, in this case, 3 paths are we going to go through, down through? Again, the word decode there is a universal word, decode. That's not my word. That's just standard lingo. And then, after the decode, it goes into the execute state, right? So again, that's everything below that horizontal bar, which is colored in red here. I've used state loosely. As you can see from the diagram, the execute state is really a bunch of states, as we previously discussed. One operation could be to add 2 numbers. Another could be to move information from one register to another. Okay, so that might be the operation at the left. And then maybe the middle operation is to move the register, the information around. Okay, but each of those paths is considered to be in the execute state, everything below that horizontal bar. Again, it's a universal word, execute, and any computer engineer or computer scientist should be very familiar with fetch, decode, execute. Fetch, decode, execute, that cycle. So the state machine is called the control unit. Everything we've discussed other than the program memory is contained within the control unit, as indicated with this beige box in the figure. Now, when you talk about the control unit, you are talking about the massive state machine. This one in the figure just happens to be really simple. But you're talking about the massive state machine within the computer that knows how to fetch, decode, and then execute program instructions. Now, in addition to program memory, we also need memory for intermediate storage. RAM, for example. Data memory is a place to temporarily store information. So when people talk about RAM, they're usually talking about this data memory. As the control unit cycles through fetch, decode, execute, fetch, decode, execute, it might need to store intermediate calculations. For example, it will temporarily store data if it's trying to add 2 256-bit strings together on a 64-bit hardware. it can only add 64 bits at a time, it's going to need to store the intermediate results in that data memory. And it'll use that in this case. Another class of things we'll need are registers. A register is basically a bank of D flip-flops that stores information quickly. It's synchronous, which means they're all the bits are moved in together, and it has enables, the registers that is, has enables to control, when information is stored. Some of the registers are dedicated, and some are general purpose. Each purple rectangle in the figure represents a register. I've drawn 3 dedicated and 3 general purpose ones, but really there are many more. I had to draw something, so I just drew 3 there. Now in this figure, in the beige box again, I've collapsed the many execution states into a single state called execution. So everything below that horizontal bar in a previous slide is now in that execution state. And you can think of the fetch, decode, execute state machine, the control unit that is, as containing its own sub-state machine within the execute state. But this is usually how it is drawn for simplicity. Now, external to the control unit, I've added another piece of hardware, called the Arithmetic Logic Unit, or ALU for short. We already gave the adder example, so we'll stick with that. The control unit doesn't have the hardware to perform addition. Instead, it communicates with the ALU, which performs mathematical and logical operations on individual bits and strings of bits. The ALU is a combinational logic circuit to perform add, subtract, shift, invert, and other similar operations. The instruction will move the add-ins in the addition example into 2 specified registers and indicate where to put them, where to put the sum, that is. So again, the instruction, I goofed that one up, the instruction will say where to put the 2 add-ins, where they're located, and then once the computation is complete, where to put the sum. The control unit, the registers, and the ALU collectively comprise what's called the central processing unit, or the CPU for short. All right, another thing we need is an input-output system. Without I/O, the CPU is pretty much useless because it can't communicate with the outside world. The I/O port system, it's a simple, it's like just simple conductors or pins that might be parallel or serial. A user does not mess with the CPU directly, only the I/O system. Now, everything that's external to the CPU is assigned a unique address. The ports in the I/O system are assigned unique addresses. The cells storing data words in memory are assigned a unique address. And the cells storing opcodes in the program memory are assigned a unique address. This is a memory mapped system. The CPU accesses all external information with a unique address. It does this with a system bus, which is just a collection of conductors allowing the passing of information. That's how computer hardware is on a high level. But let's cover a few more details of these components. Just recall that the program memory holds the opcodes. During normal execution, it's treated as read-only memory, or ROM, though you will download a program to it. Right? It's typically non-volatile and holds the program even after losing power. So there are different ways to do this. For this course, we don't need to get into it, especially right now. Data memory holds the intermediate calculations, like in the addition example. It's typically referred to as RAM, right? Random access memory, but that isn't accurate. Random access memory just means you can access any address in memory at any time. All of this memory is RAM. The accurate term here is read-write memory. That is, during normal operation, the CPU can read it and write to it. The I/O port system, as we said, can contain parallel ports and serial ports. Parallel ports are faster, but at the cost of more hardware. Serial ports are slower, but less hardware, which means less chip space, and they're usually cheaper. Remember the difference between dedicated and general purpose registers. The former are used during normal operation of the computer and are not under the control of the program, while the latter are used by the program as needed. Let's talk a little bit about dedicated registers. One type of we'll just say item that's stored in a dedicated register, or one dedicated register, we'll say that, is the program counter. And this holds the address of the next instruction in memory to execute. It keeps track of where we're at in program memory. The stack pointer is something we'll talk about later, but I just want to bring it on your radar now. It allocates memory, or the stack, that is, allocates memory dynamically. And I don't want to say too much more about it right now. The status register contains flags for certain conditions. For example, if the CPU calculates the 2's complement of some bit string, it will indicate if overflow has occurred. It also keeps track of things like carry bits and whether or not a sum is 0, which may be of interest to the CPU. The instruction register holds the opcode that is just fetched from memory. So when that state machine goes and gets that opcode, it's stored there in the instruction register. All right. This was a more detailed look at computer hardware. Next time, we're going to look closely at computer software. Thank you.